Hello all, welcome to the class. In today's class, we will be discussing about extremal points in posets. Let us start with definition. Consider a poset which is a comma r. We define the following some special elements called extremal elements. So what are those extremal elements? A maximal element of A, what is minimal element of A, what is greatest element of A, what is least element of A in the poset A comma R. We'll see that definition of a maximal element now. An element A from A, capital A, is called as a maximal element of A with following condition. If there exists no element, look at this, x is an element which does not exist actually, which is not equal to A, okay, because already you have taken A is a maximal element. There should not be any other element in A which is satisfying the condition of this. So what is the meaning of A related to R as per poset diagram? We know that the relation A is A. When you write this point with respect to diagram, x will be above A, okay. That is this cannot be maximal element because we are telling that A is a maximal element, okay. So there should not be any element of this kind. There can be x related to A because as per this definition, A comes in the maximal element position, okay. It is on top of the diagram, okay. So this is allowed but not this. So that is the meaning of maximal element. In other words, A belongs to A is a maximal element of A if whenever there is a x in A such that, look at this, A is related to x, then x must be same as A. Other way what they are telling is, if you say that there is an element which is related to this, it has to be the same element because A related to A is accepted, okay. Only this condition satisfies. There will not be any other element which is above this A. That is the simplest definition of maximal element. In the similar way, for the minimal element, the same thing holds good in reverse order, these two statements, okay. There should not be any other element which is below this. Look at this. There should not be any element which is below this. You are telling that A itself is a minimal, then and you are telling that here x is related to A. That means x is below A. That is not allowed, okay. Next, an element A belongs to A is said to be greatest element if all the elements are related to A, that means this is the greatest one. For all x belongs to A, that means for every element of A, there should be relation of this kind. All the below elements should be related to A, then it becomes greatest. It could be above the previous element, A could be above x, but sometimes there will be other element here which may not be connected to A, okay. This might be the case. You cannot say A is a greatest element because it is not connected or related by Y, it is related by X, okay. So that is the meaning of greatest. Similarly, least element is similar kind. If you say that that is the least one among the minimal element, then all above element should be related by this element. Otherwise, it cannot be called as least element among the smallest elements. So we will check that with this example. The first one is figure 1. Look at the figure 1. For example, poset represented by the following has a diagram 5 and 6. Here 5 and 6 are the maximal elements. 1 is the minimal element. Further, 1 becomes the least element and there is no greatest element, okay. That has been already done. We will understand that how it is. So as per the diagram, 5 and 6 both are called as maximal elements because they are in the same level, and all other elements here are below this. That means 1 is related to 5, 2 is related to 5, 4 is also related to 5 because we know that transitive property is there. So there is a connectivity from between all this. Next, similarly 1 is related to R, 6, 1 related to 3 related to 6, 4 is also related to 6 as per this. So this indicates that as per the definition, this is the maximal element. All rest of the elements are below this. Similarly, this also becomes a maximal element because 1, 3 are below this, and also even 4, 2 related to 6 is there. Okay, look at this. 2 is also below this. 3 is also below 5. Okay, therefore, you can say that 5 and 6 are maximal elements. Next, 1 is the minimal element. Yes, from the diagram it's so clear that 1 is the minimal element compared to all the elements because it is in the bottom compared to all other elements in the diagram. Therefore, 1 is the minimal element. Now we have to check among 5 and 6 which one is a greatest element. So as per the greatest element of the definition, least element and greatest element, to say that 5 is the greatest element, it should be related by all the elements. We have to check that yes, it is related by 1 because there is a transitive property. It is related by 2, there is a transitive property. Related by 4 also there is a direct connectivity relation, and related by 3 also there is a transitive property. But what about 6? They are in the same level but it's not related. Therefore, you cannot say that 5 is a greatest element. In the similar way, 6 is also not greatest element because 5 is not connected to this. Okay, therefore there is no greatest element. We check with the least element. We have found that only one minimal element, and you have to check whether it is least element or not. So to say that it is the least element, it should be connected to all the above elements. 1 is connected to 2, 1 is connected to 3, 2 is connected to 4 is there. There is a transitive property, so 1 to 4 connectivity is also there. Done. All 3 elements over. Next, what about 5? 1 to 4 there is a connectivity, 4 to 5 there is a connectivity, therefore transitive property 1 to 5. Okay, therefore 1 is connected to 5 also. In the similar way, 1 is also connected to 6 by the transitive property. Yes, it is satisfying that 1 is connected to all these elements which are above 1. Therefore, you can call this as a least element. 1 is the least element. Okay, in the similar way, we will check for the next example. Here, maximal elements are 5, right? Only 5 is above all these 1, 2, 4, 3, 4. 5 is above all this, and also 5 can be treated as a greatest element. Why? Because it's closed. You can also notice that one thing here, it's closed, this point is closed, therefore you are getting the least element. But here these 2 points are open, it's not closed. That's why you are not able to find out the what is that? Greatest element. Okay. In the similar way, you can cross verify here. This is the closed point, then it should have both maximal element and greatest element. 5 becomes the maximal element because it's above all this. Clearly 5 is a maximal element. Greatest, how it is greatest? It should be connected by all the elements. Yes, it is connected. Yes, 5 is connected by 3, 5 is connected by 4. It's satisfied. Similarly 2, there is a connectivity between 2, 3 and 2, 4, and 3, 5 there is a connectivity. Therefore, there must be connectivity here also as per transitive property. That's why 2 is related to 5. 5 is related by 2. So when these two are related, 2 and 1 are related, 1 is also related to 5. Therefore 5 is related by 1 by transitive property. Since 5 is related by all 4 previous elements, it can be called as a greatest element. We will check minimal element. So it's so clear that 1 is the minimal element which is below all other elements. And the next point is least element. Yes, it's a closed point or open point, we will check that. So it's closed, it's alone, right? Therefore it's connected, and it's connected from the transitive property, it's connected from the transitive property, it's connected from the transitive property. Since it is connected to all above elements, you can call this as a least element. Therefore 1 is the minimal as well as least element. This is what an explanation for both maximal, minimal, greatest and least elements. With this you have to find out for any Hasse diagram. After finding all this, there are few more terminologies to understand. What is the upper bound of a subset B of A? What is the lower bound of subset of BA? And least upper bound and greatest lower bound. So this is very generic definition that you have to understand with the symbols. An element A belongs to A is said to be upper bound of a subset. Given set is A is a set and B is a subset. If X is related to A, for all X belongs to B. The meaning of this is, to say that A is a upper bound, A must be related by all the elements, previous elements, and that element is taken from the subset. Then it's a upper bound of subset. Next is, A is said to be lower bound, then A is said to be lower bound, then it should be connected to all other elements which are all taken from the subset. That is the definition. Similarly, A belongs to A is called as a least upper bound, LUB, of a subset of subset B of A if the following two condition holds good. Since it is a least upper bound, first it has to be upper bound, find out whether it is upper bound, then there should not there is A dash is an upper bound of B, then A related to A dash. That means when you say that A is the least upper bound, among other upper bounds A should be the least. Okay, so that is the meaning of this. You have to look into the upper bounds of B because it's with respect to subset. Look at the all upper bounds of B, and the one we have selected as a upper bound A, which has to be related to all the upper bounds of this. That means this has to be the least one among all the upper bounds. That is the least upper bound. That is also called as a supremum. And greatest lower bound definition is that it has to satisfy two conditions. A is said to be greatest lower bound. First it has to be lower bound. Fine. Now among all the lower bounds, all other lower bounds should be related to A. That means all these are below A. Then this becomes the greatest lower bound among the lower bounds. Okay, that is the difference. It's called as infimum. We can check that with this example. First diagram is A, comma R, and the set is taken as B1 and B2. There are two sets taken. We will check with first B1 set. 1, 3. There is a relation from 1, 1, 3. And 2, 3. 2, 3. Why I am checking this condition is these two are my elements in the subset. I have to check with respect to subset. So 1 and 2 are my elements of B1. Therefore 1 is related to 3, 2 is also related to 3. So 3 becomes upper bound here. It's above 1 and 2. For a similar reason, in the same way you can check with other also, with all the properties, all are above this and are also related. Okay, they are all upper bounds of B1. They are all above these two elements. The upper bound 3 of B1 is such that, okay, is that satisfying the condition? 3 is my upper bound and it is related to x. X is all other upper bounds of B. Therefore, 3 becomes the LUB. What is x here? X is 3, 4, 5, 6, 7, 8. All comes here. Okay. Among all the 3 is the least one. So, least upper bound. So, LUB of B1 is 3. Next, in A, there is no element x such that it is satisfying the condition x related to 1 and x related to 2. So, to find out the lower bounds for this, upper bounds are over, right? So, lower bounds, there are no other elements here in the set A. Below 1 and 2 there are no elements. That is why there is no lower bounds at all. Since B1 is not having any lower bounds, there is no chance of getting a greatest lower bound also. Fine. For each x belongs to B2, we are moving on to the second set. We have x is related to R because 6 x is here 6 as per the diagram with the transitive property, x is related by all other elements. Okay, so it becomes upper bound. Similarly, for the same reason 7 is also related by all these elements. Therefore, 7 also upper, because I should look into this, only this part. Okay, you have to just write this is my subset here. With respect to that, with respect to this subset, 6 and 7 are upper bounds because that has been above this 3, 4, 5 subset elements. 7 is also above all this. In the similar reason, for the same reason, 8 is also upper bound. So, all these becomes upper bounds of B2. After finding upper bounds, you have to find out least upper bound. To say that any element among, because 6 is 7 and 8, all these are upper bounds, I have to just check among this which one becomes the least. 6 becomes the least, but to say that it is a least upper bound, this has to be related to rest 2 of the elements. That means 6 related to 7 must be there, 6 related to 8 must be there. Okay. Then only I can say 6 is the least upper bound. But since 6 and 7 are in the same level and there is no connectivity also, it cannot be covered with the transitive property. Okay. That is why 6 is not a least upper bound. There is no least upper bound for this. Fine. For each x belongs to B2, now we are moving on to lower bounds. So, look at this lower bound concept again with respect to subset. We have to check all the elements below this. What are all the below elements with respect to the subset? 1 is related to 3, 2 related to 3, 3 related to 3 itself. So, all are satisfying this condition. I have to, this is fixed element, to say that this is the lower bounds. Okay. Lower bounds of B2. Therefore, 1 is the lower bound of B2. Similar reason, 2 and 3, all 3, 1, 2, 3 are lower bounds. 1, 2, 3, they are all below this. Here 3 is there, 3 is related to 3 itself, though we say that it is below. Okay, since with respect to relation, you can also consider 3 there. Okay. Now here among all these 1, 2, 3, which becomes the greatest lower bound? So, if any one element which is related by all other element, then it becomes the greatest lower bound. Is that satisfying the condition? Yes, that is 3. Okay, 3 is related by all 1, 2, 3. Therefore, you can say that 3 is the greatest lower bound GLB for the second set. Cleared? So that is the definition and example for lower bound, upper bound, greatest lower bound and least upper bound for all this. So with that you can move on to the next problem. Okay, I want you to try by yourself analyzing all these definitions and do yourself. This is the answer which is there in the material also. You can cross verify and also check for this. Both problems you have to do by yourself. Thank you.